In this lesson, you will code the Monte Carlo localization algorithm in C++. Before we start, let's take a look at the problem in hand. Inside this two-dimensional map, a mobile robot represented by a blue color lives in a world of size 100 by 100. This robot can rotate left or right and move forward. The robot can also measure its distance to the 8 landmarks represented in red using rangefinder sensor. It's important to note that this is a cyclic world, which means that the robot can cross the walls and reappear from the other side. Now, we aim to estimate the robot's pose using particle filtering as it moves and senses the environment. We will be spreading virtual particles randomly and uniformly throughout the map. In this lesson, you will code the MCL algorithm in sections. First, you will move the robot and measure its distance to the landmarks. Then, you will simulate noise and add it to the measurements. Moving on, you will randomly and uniformly spread particles throughout the map. You will also evaluate the importance weight of each particle. Following, you will resample the particles. You will then generate an error value to check the overall quality of the solution. This will enable you to identify how close the particles are to the robot. By the end, you'll plot the position of the robot and the particles at each iteration of the MCL algorithm. Alright, now, let's get started. Here's the robot class with supporting and global functions. In the upcoming quizzes, you'll instantiate a robot object from this class. The instantiated robot object will have a random position and orientation based on a Gaussian distribution. Also, the forward, turn, and sensing noise parameters will initially be set to 0. To update the position and orientation of the robot, you can use this set function. To simulate noise, use this set noise function and add random noise values to the robot's pose and measurement. Now, if you want to measure the distance between the robot and each of the 8 landmarks, use the sense function. With this move function, you can rotate the robot and move it forward. Finally, you can request the robot to show you its current pose or the distances toward the 8 landmarks. There are still some other functions that we'll cover later in the lesson. Now go through the robot class and the functions in the C++ quiz section and try to understand the role of each one of them. After reviewing the robot class, print "I'm ready for coding the MCL" in the main function. Now that you've reviewed the robot class, it's time to interact with it. In this quiz, you'll learn how to instantiate a robot object from the robot class. This robot will be initialized with a random position and orientation. Then, you'll learn how to change the robot initial position and orientation. You may be curious to know where the robot is located, so you'll learn how to print its pose. Following, you'll learn how to rotate the robot and move it forward in the 2D map. Finally, you'll learn how to print the distances from the robot toward each of the 8 landmarks. Scroll down to the main function in the C++ quiz and go through the instructions. You'll notice some missing values and statements where you'll be asked to fill them out to simulate robot motion. As you know, almost all real-world sensors are noisy and require filtering. In this quiz, you'll alter the robot's pose and measurement values to noisy ones. Scroll down to the main function and follow the instructions. Now it's time for you to code the particle filter, which is the most essential step in the MCL algorithm. As we saw in the previous lesson, the MCL algorithm consists of 2 main sections. In this part of the first section, particles are generated and motion is assigned to each one of them. Here, you'll be coding this fraction by generating the particles in the first programming quiz and simulating motion to each one of them in the second programming quiz. First, you'll generate the particles. Inside the 2D map of size 100 meter by 100 meter, you'll randomly and uniformly spread 1000 particles. To replicate real-world conditions, you'll simulate noise and add random Gaussian digits to the particle forward, turn, and sensing values. Remember that each particle represents a guess of where the robot might be. Then, you'll simulate motion for each of these particles by rotating them and moving them forward. So far, you've generated the particles and simulated motion. Now, you should assign an importance weight to each one of the generated particles. At each time step, the robot is rotating and moving forward in 2D map and sensing the landmark's position. These are the actual measurements denoted by z. In order to assign weight to each particle, you need to compare the measurements of each particle, also known by predicted measurement, to the actual robot measurement. The mismatch between the actual measurements of the robot and the predicted measurements of each particle is known as the particle's importance weight. The larger the weight, the more important the particle is, and the more likely it is to represent the robot's actual position. In this quiz, you'll generate a weight vector which holds the weight values of the 1000 particles. While you were busy learning, I rotated the robot, moved it forward, and then stored the measurement values in a z vector. The z vector now holds 8 different values, each of which represents the actual distance of the robot toward one of the 8 landmarks. Also, I've included a measurement probability function which takes the actual measurement vector and compares it to the predicted one. This function will compute the probability of how close the predicted measurements are to the actual ones. Note that noise is always added to the measurements. Now go ahead and code the importance weight right after the block of code where you generated particles and simulated motion. You've successfully coded the first section of the MCL algorithm, known as motion and sensor update. Now it's time to move to the second section, known by resampling, and code it. But before you start, let's first learn how particles are resampled. Given a set of n particles, ranging from 1 to n, each particle has a pose composed of an x position, y position, and theta orientation. In addition to the pose, each particle has a weight denoting how close the particle is from the robot position. Let's sum all of these weights and call the sum capital W. Then, let's compute the normalized weights alphas by dividing each weight by the normalizer capital W. Alpha is the probability of each particle being selected from the whole. The sum of all the alphas is equal to 1. The resampler will group all n normalized weights in a bag. Let's assume that particle 2 and 3 have large weights. The resampling process will happen n times, picking a particle from the bag every time. By the end of the resampling process, there will be the same n number of particles as there were originally. But which particle stays or go will change. At each iteration, the resampling process is more likely to pick particles with large probabilities. This process happens randomly, but is always more likely to pick particles with higher probabilities or alphas. Here, P2 and P3 were selected more than once in the new set because of their high probabilities, and P4 was selected only once because of its relatively low probability. Now suppose that you have 5 particles, each with an importance weight. Compute the probability of drawing each particle in the new set. Use the C++ coding section and follow the instructions to print the results. Let's have a closer look at how particles are being picked. In this example, we are giving a set of 8 particles, each with its specific weight. These particles are initially grouped in a wheel, with each particle occupying a space depending on its weight. We can notice that particles 1 and 3 occupy a very small space because of their small weights, whereas particle 4 occupies the biggest space because it has the largest weight. Initially, we randomly pick an index from the set of particles ranging from 1 to n, or in our example, 1 to 8. Let's pick the 6th particle as our initial index. Next, we will initialize a variable called beta and give it an initial value of 0. Now, we are going to iterate over the set of indices, and for each index, we will compute a new beta by adding to it a uniform random value ranging from 0 to 2 times the largest weight, in this case 2 times W4. As you can see, the new beta is now equal to the size occupied by particle 6 plus half the size occupied by particle 7. While W index is smaller than beta, we should subtract the W index from beta and increment the index. Here, you can see that the size occupied by particle 6 is smaller than the size of beta, so we'll subtract W6 from beta and increment our index. Beta size is now reduced to only half of the size occupied by particle 7, and the index is now incremented and shifted to particle 7. Now, if beta size becomes smaller than W index size, we'll have to pick the particle at that index. Here, you can see that beta is smaller than W7. Therefore, we'll pick the particle 7. After that, we iterate and compute the new beta. Note that sometimes you will pick the same particle more than once because of its small value. Now that you've learned the resampling pseudocode, try to code it with C++. You've just coded the MCL algorithm, and now you should evaluate the overall quality of your solution. To do so, you'll need to compute the average distance between the particles and the robot. A good solution will result in an average distance smaller than a meter. Before we start, let's iterate the MCL algorithm 50 times. At each iteration, we'll see how the quality of the solution is affected each time the robot updates its pose and takes new measurements. Here, I'm providing you with the evaluation function which take the robot pose and the particle set as arguments. Inside the evaluation function, I'm comparing the x position of the robot with the x position of each particle. I'm also normalizing the values since the robot operates in a cyclic world. After that, I'm comparing the y position of the robot with the y position of each particle. Here, I'm not taking into consideration the orientation of particles since the measurements are not affected by the robot or particle orientation. Moving on, I'm computing the Euclidean distance of the differences. And finally, I'm computing the average error of each particle relative to the robot position. Now, use the evaluation function and compute the average distance or error at each iteration. So far, you've coded MCL and evaluated the overall quality of your solution. Now, you'll be able to visualize what you've coded, or more precisely, MCL in action. To do so, I'm providing you with the visualization function, which takes the number of particles, the robot's pose, and particles at each time step as arguments. Note that the plotting functions used here are linked to the Python matplotlib library. Initially, I'm formatting the graph by including a title and specifying the x and y limits. Then, I'm plotting the original particles with green circles, and the resampled particles with yellow circles. Following, I'm plotting the 8 fixed landmarks with red circles. Moving on, I'm plotting the robot position, which is our main point of interest, with a blue circle. Finally, I'm saving the plot and destroying it. Unfortunately, you'll not be able to run this program in the classroom yet, so follow the instructions and then edit and run the code. Initially, 1000 particles are spread randomly and uniformly in the 2D map. We can see that the average error is very high since particles are distanced from the robot. Then, after few iterations, the average error is reduced. But we still need to iterate since the particles are not precisely estimating the robot's pose. Finally, after many other iterations, the average error is reduced tremendously and particles are now localizing the robot. Congratulations! You've just coded MCL in C++. Now you can upload this code to any real-world mobile robot with rangefinder sensors to estimate its pose in a known map. You've probably noticed that the average error changes every time you run the program. This is because MCL is a probabilistic estimation. Now share with your classmates the number of steps it took you to achieve a converging solution. In the upcoming project, you'll use ROS and implement the adaptive Monte Carlo localization package. Don't worry, I know that you're not familiar with AMCL yet, but stay tuned to learn it.